Good morning, and thank you for joining us today. My name is Bertrand Irisu. I am the CEO and co-founder of Brainome. And welcome to our fifth webinar on the benefits and applications of our measurement-based approach to machine learning. Before we get started, I'd like to remind you that we do have two webinar series running concurrently. Today's is on the benefits and applications of our tools. We also have a Cortex series that's running on a weekly basis, and that covers more of the math and the fundamentals behind our measurement. And please feel free to sign up for them at brainome.ai/resources/events. Also, if you have any questions during this seminar, please put them in the Q&A channel, and we will answer them at the end of the webinar. Our topic today is about the benefits and applications of compact and explainable models. It will be presented by Lynn Chase. Lynn is our VP of Product Management at Brainome, and she's laser focused on making our Dimension users successful. She earned her PhD in computer science at Carnegie Mellon in 1997, and she's been working on making AI software useful in the real world since then. She joined us a few months ago, bringing with her really an extensive multi-decade track record of successful deployment of AI technology in business environment. Without further ado, Lynn.
Thank you for the introduction, Bertrand. As Bertrand mentioned, today we're talking about the benefits of working with dimensions with respect to how compact and how explainable the models are. In order to understand that, I'd like to start with a little bit of context. So I'd pose this question to you. When you're working on a machine learning project, how can you predict how much money, effort, CPU, memory, I/O, data do you need to budget for that project? And until dimensions came onto the scene, the answer was basically there is no answer. What's going on in the industry and in the community at large is a culture and a set of practices that amount to a belief that more is always better. More data will always be better, spending more compute cycles will always be better, and putting more parameters into your model will always be better. And we'd like to really shine a light on that and really ask the question, particularly today, with respect to, is it really true that more parameters are always better? We say no. We say, look at our approach, look at how we do things, and take a look at what the benefits are of building compact models and building them very fast. So that's what the context is for today's discussion. Just a little more context. As a reminder that what we consider to be excessive use of resources is pervasive and has a pretty arbitrary flavor when you look at what's going on in the machine learning world today. A simple example of this is that the models that have been built to do a state-of-the-art good job on ImageNet, they vary significantly in terms of the total model size and the total amount of computation needed in order to create those models. So that alone should make you scratch your head and wonder, is bigger really better? And we are here to say we do not think that bigger is better. There are a bunch of reasons why we think this is true. The first is not everyone has unlimited resources. So many teams work in an environment where you can't just write a blank check for the data, for the compute, for the human resources that you need in order to do these projects. A second one, which I would argue is possibly even more important, is that if you can't predict the costs, then you can't create systematic success. If you really want supervised machine learning to become a core part of how you're working with your data and how you're delivering products and services to your customers, unless you can actually have a systematic, measurable way to predict what's going to happen, it's going to be really hard to succeed. Some of the things we're seeing in the real world with supervised machine learning are that the big models that people are producing, they're hard to deploy and they're hard to maintain. So AI ops, it's a rat hole right now, just very, very complicated. And big models are also hard to explain, and that has its own set of problems associated with it, which we'll talk about a little bit more as we proceed in this webinar. So I want to encourage you, if you haven't had a chance, to take a look at the archived versions of other webinars that we've presented. In particular, the Core Tech series is really good. The Core Tech 101 goes over conceptually how it is that we do measurements on data against different types of models. And then Core Tech 201 goes into all of the math and all of the algorithms behind what's new here with Brainome and the Daimensions product. And there's still one more 301 that's going to be run on Tuesday. You can either come join us live to get a summary of all of the information about the math and the algorithms, and then see a whole bunch of examples being demonstrated, or you can go and look at the 301 archive on the website. But the bottom line is that what Brainome is bringing to the game and what Daimensions puts into your hands in the form of a very easy to use software product is the ability to measure the learnability of data against different types of models. And this can all be done before models are built. And the consequences of all of that are manifold. You can know when you have enough data. You can know when you have the right data features. So it's a great tool for doing data feature design. And there's a whole webinar just on that. There's a Superpower Your Data Prep webinar that you can go take a look at that goes into that in detail. You can know if you're going to overfit. You can estimate if you're going to overfit before you build the model. And after you build your model, you can know whether or not you did overfit. And that's a game changer in a lot of different application domains. You can know which of your data attributes are the most important using the attribute ranking capability that we have in the Daimensions product. And so we can figure out which of the data attributes that you've provided in your data set are actually contributing the most to the predictive power of the model that you'll build eventually. You can figure out which kind of machine learning model will work best with your data, and you can estimate how long it will take to train. Daimensions currently supports decision trees and neural networks. So what does all of this mean in terms of the discussion around compact and explainable models? Well, this is kind of the key idea. In order to get to a small and effective model and get there quickly, you want to go through this process of iterating very quickly through various data options, changing the amount, incrementing the amount of data that you're looking at, making incremental changes to what the data features are that you're extracting and using in your modeling, and very quickly using our measurement techniques to find out when you have enough data, when you've got the right data features, which data features are actually creating the outcomes that you're looking for, and to know whether or not you're getting close to that red borderline of whether or not you're going to overfit. And it's this iteration process that allows you to find the smallest effective model for you to build and then use as a predictor. So let's take a look at what we mean by compact. I'm going to show you a very detailed chart. My apologies in advance for all of the numbers on the screen, but I wanted to get this across through some pretty detailed explanation. Here on this chart, we have a list of representative problems that you can see in the OpenML collection of well-known and respected state-of-the-art problems in machine learning. And what we've got here, this is a description of how many features there are in each of those data sets and how many instances or rows there are in each of those representative data sets. What we've got here is the size of the model that Google's AutoML would create in order to build a solution, in order to build a predictor for that data, compared to Brainome's model size. And AutoML is not the only other tool out there. It's just something that is, we feel, a very fair comparison in terms of AutoML representing from many perspectives what the state of the art is in terms of how supervised machine learning is done. The Brainome results comparatively are really impressive. This is the size of the AutoML result itself, and this is the size, then that's in megabytes, and this is the size in kilobytes of the Brainome model that solves the same problem. And you can see that over this particular set of examples, we see 3 orders of magnitude smaller. Now that is not, that's a one representative sampling of one set of problems from OpenML. I can tell you more anecdotally that what we're seeing in working with customers in the field is that we're very consistently getting 2 orders of magnitude smaller models, and sometimes 3. So what we tell people is you can expect that you're going to see 100 time reduction in size. And along with being more compact, because what we're doing, and this is again covered in detail in the Cortec webinar series, so I'm not going to go into a lot of detail here, but because we're essentially building custom models from the ground up using our measurement tools, using the dimensions measurements, we're building right-sized models that represent, they have the number of parameters in them that are needed in order to represent the extractable rules and patterns in the data that's been presented. And because we end up with smaller models, we also get to them much faster. Smaller and faster go hand in hand because of the approach that we take. And again, same representative set of samples drawn from OpenML. The Google AutoML results in time, again here measured in hours versus in Brainome in seconds. We see 2 orders of magnitude faster. So we're consistently telling people that they can expect 100 times faster and 100 times smaller when they work on their data sets with our tools. So that's compact. Oh, I wanted to, before I go on to explainable, I wanted to just say a few words about where compact really matters. It doesn't matter to everyone. The size of the model doesn't directly impact the usability of a predictor in all cases. But in the mobile device world, in the IoT world, and in anything related to mobile edge computing, this is an absolute game changer. So we're seeing obviously applications in the telecommunications world. We're seeing applications in agriculture. We're seeing applications in field maintenance of infrastructure. So this is a big, highly impactful improvement in what's available in those kinds of applications. The next thing that I wanted to talk about is explainability. There are really 2 ways that explainability is greatly improved when you take Brainome's approach and use the Dimensions software. The first one is that the product that Brainome has created, Daimensions, is a compiler. It takes data in and it writes out a predictor. It writes out Python code. And that Python code is a standalone, usable piece of code that is just really compact, and you can open it up and take a look at what's inside. It's human readable. And because the models are often very, very compact and very small, taking a look at what the written code is that actually does the computation to provide the predictions can be very insightful. So let's take a look at an example of that. We have, in this case, a data set that represents the distinction that is needed to be made between benign and malignant tumors. And the data set had 482 patients in it. And the features that are listed here were features that medical experts had chosen because they believed they had predictive capabilities for cancer. So there's sort of a curated set of 9 features that were in this data set. With Brainome, we're able to get to very quickly get to a 96.8% accuracy on this data set, which is a great number. And what I want to show you is, again, just a quick reminder, that data, 482 by 9 plus 1 additional column for labeling of benign or malignant, got put into Dimensions, and out came a Python predictor. And this is the code that you can just read and see. It creates a 2-neuron solution. It's a very compact 2-neuron model. And this is the code that shows how the predictor actually does its calculation. And you don't need to know this, but I'll just show you anyway. H0 is one of the neurons, H1 is the other neuron. And here you can see the inputs. That's column 1, column 2, feature, etc. These are all the features. And this is the calculation just in a simple piece of code. So this kind of explainability is super important for applications where there's any kind of regulatory body involved in being able to prove to the regulatory body what it is that the machine learning system is doing. So for instance, the FDA really cares about explainability when it comes to using supervised machine learning to create products that are going to impact patient care. So if the developers of a product that's trying to determine benign or malignant tumors want to prove to the FDA that this is a workable solution, then being able to have human readable output from the predictor that is simple and easy to understand and can be tracked over time as training changes values is extremely, extremely valuable. And the FDA is starting to accept that this kind of explainability is reliable. This could also be equally useful, this type of explainability where you can just sort of take the lid off of the Python predictor and really just look at the code and look at the computation in a closed form solution, is also going to be very useful in domains such as insurance, where underwriters have to prove to their regulatory bodies what exactly the systems that they're using are doing when they're making underwriting decisions. So that's the first kind of explainability. The second kind of explainability is a direct result of using our attribute ranking. And this is something that has been demonstrated and gone into in a lot of detail in some previous webinars, but I want to go over it here again, but this time from the perspective of, well, what if I just want to be able to explain what my model is doing? So I'm going to try to make this a little bit bigger. See if we can make that a little easier for everybody who's following along at home to see. So the first thing I'm going to do is tell you a little bit about a data set that we often use to demonstrate what's going on with Brainome, which is the Titanic data set. And this data set contains information about passengers on the Titanic and whether or not they survived. And the kinds of features that are in this data set are features that have to do with the sex or gender of the passenger, how many children, parents, siblings they had on board, whether or not they had a first class ticket, what they paid for their ticket, what cabin information there was. So the kinds of things that would show up on a shipping manifest or on a passenger manifest for a shipping line. And then of course the outcome is whether or not that passenger survived. So I'm just going to show a real quick run of dimensions on the Titanic training set. And this is running in real time. And I'll just very quickly go over some of the information that we've discussed in more detail in previous webinars. You can see that we have 891 passengers in this data set. There were 11 attributes. The classification is binary, and class balance is 61.62% who did not survive and 38.38% who did. The capacity progression, which shows the learnability of the data, looks pretty good. And we're definitely in that middle yellow zone on learnability. So that looks good too. And just vanilla out of the box, no tuning, no special parameters, no special requests to the software to do anything specific. We got 79.12% accuracy. Now, we know from many people having worked on this data set that that's not quite as good an accuracy as you could get. But let's also take a look at the generalization ratio. It's pretty good, 2.9 bits per bit on a binary classifying predictor with relatively balanced data. That's a good generalization ratio. So I believe that just the vanilla model that was built running the software with no particular parameters or additional requests came out pretty well. Now, let's think about this from an explainability point of view. Right now, we just know we have a pretty general model and we are getting, close to good enough accuracy. We know we could probably get a couple more points out of this. But we don't really have a sense for what the model is doing. So what we can do is we can run this again, but we're going to ask the system to rank the attributes. So of the 11 attributes that are being analyzed, we're going to ask the system to tell us which ones actually matter. And this is where we get into some interesting explainability. So the very first thing that happens when you run with minus rank is that the attribute ranking tells you what are the important columns that are being used to make the predictions. And this is super interesting because it tells us that we've got sex or gender. We've got 2 family parameters having to do with the number of siblings and the number of parents. And we've got the class of the ticket that was being used. So whether it's first, second, or third class ticket. And this tells us, this is directly in line with what we knew actually to be true at the time of the Titanic disaster, that women and children with first class tickets got off the boat first. And so that's where the survival rate comes from. And you can see that by using attribute ranking, you get really great insight into what exactly the model is doing to predict the outcomes. So that the use of attribute ranking combined with the being able to build a compact, simple model and then sort of take the lid off the top and look at the code, that's what creates explainability in our world. And again, explainability, super important. It's important to everyone, but it's super important in applications where there are regulatory agencies involved. So that's the fundamental story about compactness and explainability. I'll just remind you that the bottom line is that Daimensions is a compiler and it builds models that are right-sized based on the measurements that Brainome has brought to the industry, the new measurement-based approach to supervised machine learning that's now available through Brainome. We create models that are at least 100, on average, at least 100 times smaller, sometimes much smaller than that, and 100 times faster. And there are 2 different ways that you can get explainable results out of the approach. And that is the story.
Lynn, thank you for this presentation. We have a few questions in the Q&A section. And if you still have some more, please feel free to go and put them in there. The first question is from Rich. It was asking, why are your models smaller?
That's a great question. And the fundamental answer is because we build from the ground up. We look at we have these new measurement capabilities, which again, I encourage you to learn about by checking out the Core Tech webinars. But we have these measurements that are used to help us construct models from the ground up. We put the number of parameters into the model that are needed in order to get the generalizable results, to be able to represent the predictions that the data can represent. And we don't arbitrarily start with some large number of parameters and then spread learned information over those number of parameters. We build from the ground up. So you basically get a tailored model that has the right number of parameters in it, and that's why it's compact.
Okay. Second question's from Igor. What software and hardware are required to run the models?
Oh, that's a great question. I'm sorry I didn't cover that earlier. The basic picture is you just need generic Python with some very simple libraries. You don't need PyTorch, nothing, there's no TensorFlow stuff happening. And you can run on any generic hardware. So, we'll run on laptops, Mac OS, Linux, Windows. And most of the time you don't even need a GPU. You can just run on generic hardware.
Okay. I see the last question here from Angie. What data pre-processing is required to use the models?
Oh, that's a great question. I'm going to answer that in two parts. One is just a reminder about what our data requirements are, and then I'll answer the pre-processing question more directly. The the data requirements that we have is that you put your data into a CSV file, and that file be of fixed dimensionality, meaning that every row has the same number of columns. Side note, it's okay if there are some values missing, but the point is it can't be the case that every row has a different number of columns. Every row has to fit into the fixed dimensional framework. Other than that, no limitations. No limitations on the number of columns, no limitations on the number of rows or instances. In fact, no limitations on the number of labels for multi-class classification. Okay, so that's the fundamental data situation. But the pre-processing thing is actually super interesting because we do all the pre-processing, and that Python code that comes out of the Dimensions compiler actually has all the pre-processing built into it. So you don't have to do anything. You can just feed in a new CSV file, and that Python predictor, that tiny little compact Python predictor that we output, will handle all the data pre-processing for you. Good question.
Great.
Yeah.
That was the last question. Thank you, Lynn. So that's all for today. I'd like to remind you that we have one more webinar in this series next week on easy ops deployment, or easy and tiny ops deployments. And again, we encourage you to sign up for this or our Cortex series. We do also have the pre-recorded webinars that happened previously available, so you can watch them again if you'd like to. Also, we'd like to, if you are curious about our software, please feel free to register online to try. We have a demo you can try just without signing up, or you can sign up to get basically more capability from our online version of the software. And of course, if you have any question, you can reach us at support@brainome.ai. Thank you again for attending our webinar today, and hopefully see you all next week.